Optimization Part 6. This is a particularly easy problem, and I thought I would throw it in here as a breath of fresh air. Let's read the problem first. Rectangles beneath a semicircle. A rectangle is constructed with its base on the diameter of a semicircle, with radius 5, and its two other vertices on the semicircle. What are the dimensions of the rectangle with maximum area? So what I have here is my semicircle of radius 5. Just the top half will make this easy. And then the rectangle they speak of. And I am going to let x be, try that again. I'm going to let x be this length here. That means the base is 2x. But I want x to be a non-negative number. And then I'll let y be this amount here. So the area of the rectangle, our objective function, looks like this. The area equals base times height. And our base is not x, but it's 2x because these are negative values. I didn't want to count that. So this equals 2x times y. Now, as with everything else, I need to get a connection between x and y. And the connection is that the circle, let me draw this in here, or let me write it, circle of radius 5 has equation x squared plus y squared equals 5 squared. Then I'll solve for y, so I'll subtract x squared from both sides. So y squared equals 25 minus x squared. And then I'll take the square root. Y equals plus and minus the square root of 25 minus x squared. Now, this would be for the whole circle. That means the top half would be the plus and the minus would be the bottom half if there was one, but there is none there. So the equation that I actually want is just the positive version. So let me get rid of the plus or minus. So this is what I'll use for y. And then I have a equals 2xy, and now I'll substitute this expression in here. So if you remember, this thing here is referred to as the constraint. And in fact, once I plug that in, I'll have a function of x alone. Now, before we do anything, you should determine what values of x are applicable here. I said x, I wanted to be the positive on the positive side of the y-axis. Theoretically, the smallest x could be is actually 0, which means the rectangle would just be a thin segment from the origin to the top of the circle. Or x could be up to 5. If it was 5, then you'd have a thin line along the base. So the domain for this problem is that 0 is less than or equal to x, which is less than or equal to 5. And also note that a of 0 equals a of 5 equals 0. The area when x is at any of these extreme points is going to be 0. As you can see by the picture even. If x was 0 and I just had a line segment, that has no area. If x was 5 and I just had a horizontal line segment, that has no area either. So, no matter what happens, whatever critical number I find in this interval will be the one we're looking for, because these are going to be positive numbers in this interval. X squared it's going to be between 0 and 5, so this thing inside of here will be positive. If x is positive, this will be positive. The whole thing will be positive. So, I don't even have to check to see if it's a maximum. It's going to automatically be one. And so, to find out what that is, we take the derivative and set it equal to 0. I'll use the product rule. First thing I'm going to do is take the derivative of 2x, which will be 2, And then I will leave the 2x alone, plus 2x times, take the derivative of the square root. We get 1 over 2 times the square root of 25 minus x squared. But this is a chain rule situation. We've got a function inside of the square root. So I got to take the derivative of 25 minus x squared. That will give me negative 2x. And we're going to set that equal to 0. Now, one of the things I'm going to do right off the bat is simplify a little bit if I can. Like, for example, I'll take this 2 out and this 2 out. And let me rewrite what I have then. 2 times the square root of 25 minus x squared minus 2x squared divided by the square root of 25 minus x squared. And that's equal to 0. And I think I've done this 1 or 2 times before. I'm going to multiply everything by the square root of 25 minus x squared. So if I multiply the whole thing by the square root of 25 minus x squared, let's put big old parentheses around everything to let you know what I'm doing. For this piece, I'll get 2 times 25 minus x squared. Minus, this is the beautiful part. This square root here, when it multiplies to the second piece, will clear that denominator completely. And you'll have minus 2x squared equals 0. Now, like normal, I'll combine and do all the other stuff. I can't help it. I'm going to divide by 2 right now. I can't stand it. It's so easy to do, I'm going to do it. So what do I have left over then? I have 25 minus 2x squared equals 0. And so 25 over 2 equals x squared. And divide, or take the square root of both sides. Forget about the negative square root. I will get x equals the square root of 25 over 2. Or if you want, you can write that as 5 over radical 2. So now, if you remember, my rectangle had the dimensions 2x plus y. And they are asking us, oh, this is one thing you've got to pay attention. I tend to not pay attention to a lot. What are the dimensions? That's what they're looking for. They're not looking for the maximum area. They're looking for the dimensions that give the maximum area. So I have x. Then what is y? Y equals the square root of 25 minus x squared. So I'll put 5 over radical 2 squared. That will equal the square root of 25 minus 25 over 2. So that'll be the square root of 25 over 2, which is the same number we got for x. Y is the square root of 5 over, or is 5 over the square root of 2. So then our dimensions are, now remember we wanted not just x but 2x. So I'm going to have 2 times 5 radical 2, that'll be 10 over radical 2. And we'll use this not as an x, but as a by. 10 over radical 2 by 5 over radical 2. And there you have it.